Okay, class. Today I want to go through section 3.1, and 3.1 is about derivatives of power functions and exponential functions. And what we'd like to be able to do in this section is not have to rely on the definition of the derivative as much when we go to find derivatives of functions. So for example, what we've done so far in class is something like if f of x was equal to, let's say, x squared plus 3x plus 2, and the question was to find the derivative of that function. Well, we had to go to the limit definition and say this is the limit as h approaches 0. And then we said this was the function evaluated at x plus h minus the function divided by h, which is the same as saying the limit as h goes to 0. And then this f of x plus h just means substitute in x plus h for all the x's. So you'd have x plus h squared plus 3 times x plus h plus 2 minus the function x squared plus 3x plus 2, and then all that divided by h. And then we've done this several times where we now just simplify the expression, so we get the limit as h goes to 0. Expand this, and you got x squared plus 2xh plus h squared, 3x plus 3h plus 2 minus x squared minus 3x minus 2, and then all of that divided by h. So we get the limit as h approaches 0, and typically what happens is you get some stuff to cancel out. So those cancel, and those cancel. And then everything that's left has an h in it, and then we factored out the h. We were left with 2x plus h, just h, plus 3, and then all that divided by h. Cancel, and we ended up with the derivative was equal to 2x plus 3. All right, and then the nice thing about this, once we got it in this form, is we could say, well, what is the derivative evaluated, let's say, at 4? And so we take 4 and plug it into that derivative, and we get 2 times 4 plus 3, and we get 11. Okay, and so then I could just plug in any number. If I said, what's the derivative at 1? I could just plug 1 in and so on. All right, so getting to this point is makes it a lot easier when you're going to just take the derivative at different places then. All right, so what I'd like to be able to do is I'd like to talk today about how we can get from here to here without having to do all of the stuff in between. All right, so I kind of want to generalize what's going to happen here if I take the derivative of a function that maybe looks something like this one up here. All right, so let's take a look at an example. Suppose that I wanted to find, I'm going to use this notation, the derivative with respect to x of x squared. All right, and I think we did this in class, and we said this is the limit definition would be the limit as h goes to 0, and then it was x plus h squared minus x squared all divided by h. So you get the limit h goes to 0. This expands to x squared plus 2xh plus h squared minus x squared all divided by h. The x is canceled out. There's a common factor of h in here. We factor that out, and we were left with 2x plus h over h, and then we had the limit as h went to 0, and you ended up with this answer was 2x. Okay? All right, so what I'd like to be able to do then is look for how do we get to here so quickly. All right, and what I'd like to do is I'd like to look at this more in general and say, well, what happens if we wanted to take the derivative with respect to x of just say x raised to a power? All right, so by definition, this is going to be the limit as h goes to 0, and then we're going to have x plus h to the n minus x to the n. All right, I'm going to make my h's a little bit taller so I can tell the difference between the two, between the h's and the n's, and then all divided by h. Okay, so what I want to look at then is this thing here, this x plus h to the n power. And I want to look to see if we can come up with some kind of a pattern there. And so if we said x plus h to the second power. All right, we saw that up above here. That expands to x squared plus 2xh plus h squared. If you were to take x plus h to the third power, your expansion would be x to the third, and I'm just going to tell you what you're going to get when you multiply this out without having to go through all the algebraic manipulation. You're going to get that, plus you're going to get 3x squared h plus 3xh squared plus h to the third power. And if you take x plus h and raise it to the fourth power, the expansion is going to be x to the fourth plus 4x cubed times h plus 6x squared h squared plus 4x h to the third plus h to the fourth. All right, and then I'm going to tell you that when you take x plus h to the fifth power, you're going to get x to the fifth plus 5x to the fourth times h plus 10x to the third times h squared, and then you're going to get a bunch of terms after that. All right, and so what I want to look at is, well, what's going to happen then if we take x plus h and raise it to the nth power? All right, well, I think we can see a pattern here that we're going to end up with x to the n will be our first term. And then if you look at these second terms all have a coefficient that this one is a 2, this one is a 3, this one is 4. So it looks to me like this is going to be plus nx to the, and then this looks like a 1 less power, and then times h. And then if you look at everything that's left over here, everything that's left over here is going to have at least a common factor of h squared, and then some other junk left over. Okay, for example, if you factor out an h squared here, you're going to be left with 3x and an extra h. If you factor out an h squared here, you're going to be left with 6x squared. You're going to be left with 4xh, and you're going to be left with an h to the third. So there's going to be some extra junk here. All right, so if we go back up to this limit, then the derivative is going to end up being something like x to the n plus nx to the n minus 1 times h plus h squared and then some junk, and then minus the function, which was x to the n, and then all of that divided by h, and then the limit as h goes to 0. Okay, so we're going to end up with a similar thing happening here that's happened before, and that is these are going to cancel out. And then if you notice, everything that's left out in here is going to have an h in it. And so you're going to get the limit as h goes to 0. If you take an h out of here, you're going to be left with nx to the n minus 1. And if you take an h out of all of these terms, you're going to be left with h times all that extra junk, and then divided by h. Right? And then as h goes to 0, those are going to cancel. And then as h goes to 0, you're going to be left with nx to the n minus 1. And then as h goes to 0, all of this extra stuff is just going to go to 0. Right? And so you're going to be left with this expression. Right? Now you're going to find that this is a very powerful thing to get to an answer, because now we're saying that if you take the derivative with respect to x of x raised to a power, we just established that you can say nx to the n minus 1 power. All right, so there's a whole bunch of functions here that we can take derivatives of then. So for example, if I wanted to take the derivative with respect to x of x to the, let's say, the third power. Okay, I don't have to go through and use that limit definition anymore. I can just say, oh, the derivative of this is, well, the power is 3. So 3x, and then I'm going to decrease the power by 1, and we end up with that's just 3x squared. If I wanted to find the derivative with respect to x of x to the fifth power, okay, I don't have to go through the definition of the derivative and take x plus h to the fifth power. I can just say, pull down the 5, raise that to the fourth power, and I'm done. Okay, so if I wanted to know, let's say, you've got the graph of y equals x to the second power. And the question is maybe find the equation of the tangent line at x equals, let's say at x equals 1. So I know the first thing I need to do is find the slope. The slope is going to be the derivative of the function at 1. Well, we can find the derivative now pretty quickly by using the power rule. Power rule says bring the exponent down, make the power 1 less, right? So this is going to be just 2x to the first power. All right, now this isn't the equation of the line, this is just the derivative. If I want to find out what the slope is, now I got to take 1 and plug it in here, and you're going to get 2 times 1, and 2 is the slope. All right, now in addition to finding the slope of the line, I also need to know a point that's on the line. All right, and you're going to be given a point like this. It says find the equation of the tangent line at x equals 1. So we know that x is going to be equal to 1. All right, but then we want to know what's the y-coordinate. All right, so we're looking for something that looks like this. Here's the graph of y equals x squared. Here is x equals 1. I want to find the equation of this line. Okay, so a point that's going to be on the graph would be when x is equal to 1, y is going to be equal to what I get when I plug 1 in here, and we're going to get 1. All right, so now the question is, what is the equation of the line that goes through this point that has a slope of 2? And so I think a lot of you did this. Y minus the y-coordinate equals the slope times x minus the x-coordinate. And then just wrote this as y minus 1 equals 2x minus 2. Bring the 1 over, and your equation is just y equals 2x and minus 1. All right, and so the equation of that line ends up being just y equals 2x minus 1. Okay, so here you've got a whole family of different kinds of functions that you take derivatives of. I want to also mention here that you can also take derivatives of things like, what is the derivative with respect to x of, let's say, 1 divided by x squared? All right, now a common thing for people to want to do on this is to say 1 over 2x. All right, and that's not going to be the case. This is not 1 divided by 2x. What you want to do is you want to make this look like x to a power. All right, and if you remember your rules, when you have a x squared in the bottom, this is the same thing as saying the derivative with respect to x of x to the negative 2 power. All right, and then you can apply the power rule, and the derivative of this is bring the power down, so you get negative 2x, and then we need to decrease this by 1. So if you take negative 2 and you subtract 1, you're going to get negative 3. All right, and so the derivative here you could rewrite. It's okay with me if you leave it like this, but I think the back of the book is typically going to rewrite this as like negative 2 divided by x to the 3rd power. Okay, so don't apply some rule that doesn't apply. You have to write this as a power function first, and then you can apply the power rule. Okay, another nice application of this is you might have a function like f of x is equal to the square root of x. All right, and if you remember your rules for square roots, this is the same thing as x to the 1/2 power. All right, so if you wanted to find what is the derivative with respect to x of the square root of x, you could write this as the derivative with respect to x of x to the 1/2 power, and then apply the rule. It says bring the power down times x, and then take 1/2 minus 1. 1/2 minus 1 is 1/2, negative 1/2. And then again, your book is probably going to rewrite this as there's the 1/2, and then x to the negative half is the square root of x in the denominator. Okay? All right, so you've got a whole bunch of different kinds of functions you can take derivatives of. All right, some of the other rules in this section I think are a little bit more intuitive, and one of the rules is what is the derivative with respect to x of a constant? Okay? All right, now I think that one thing you can do with this is you could say, well, the derivative of a constant is the slope of the tangent line. So let's say that the constant is like 3. So let's say that this is a line at x equals 3. That line is going to be horizontal. All right, and then if you look at, well, what's the derivative at any point? The derivative is the rate of change anywhere, and you should recognize that the derivative of a constant then is going to be just the slope of a horizontal line, which is 0. All right, another one is the derivative with respect to x of just x. Okay, so here again, you could be thinking, well, the line y equals x looks like this. The derivative is going to be the slope of that line anywhere, and the slope of that line is just going to be equal to 1. Okay, you could also use the power rule on this one and say this is the derivative with respect to x of x to the first power. That says take the power down is 1, and then x, and then decrease 1 is x to the 0, and x to the 0 is 1. Okay, so you're going to see these somewhere in there as well. All right, now what I would like to be able to do is come back to the first problem that we looked at, which was this one, to find the derivative of a polynomial, and I want to end up getting to the 2x plus 3. All right, but before we do that, there's a couple of other rules we need to look at. One of them is the constant multiple rule. All right, so let's say that you've got the derivative with respect to x, and you have a constant times a function. Okay, I think this is fairly intuitive what you're going to do, but I want to look at this in terms of the definition of the derivative. The definition says take the limit as h approaches 0. This is going to be c times f of x plus h minus c times f of x, all divided by h. Well, you can rewrite this as the limit as h goes to 0, factor out a constant, and you're going to be left with, in the numerator, f of x plus h minus f of x, all divided by h. And then we had a rule that said if you take a constant times a function, you can pull that constant out. And so you're going to get that constant, and what you're left with is the derivative of the function. All right, so the constant multiple rule is you're going to take the derivative of the function, and then all you're going to do is multiply that answer by the derivative, or by the constant. All right, so here's an application of that. It would be find the derivative with respect to x, and let's say we wanted to take the derivative of like 4x to the 5th power. Okay, so this is a constant times a power function, so our rule would be take 4, and then take the derivative of this, 5x to the 4th, and then we would end up with just 20x to the 4th power. Okay, so essentially you could jump to here pretty quickly by just saying take this, multiply it by the constant out in the front, and then decrease the power by 1. Okay, so derivative of a constant times the function, again, I think it's fairly straightforward. Okay, the other thing I want to look at is what about if you take the derivative and you've got two functions added together. Let's say a function f of x and another function g of x. All right, well, by definition, this is going to be the limit as h goes to 0, and then I'm going to plug in the function evaluated at x plus h would be f of x plus h plus g of x plus h, right, and then minus the function f of x plus g of x, and then all that divided by h. All right, and then I'm just going to rewrite this another way and say this is the derivative as x as h goes to 0. I'm going to say let's write this as f of x plus h, and then we got a minus f of x over here, and then we've got plus g of x plus h, and then we've got a minus g of x. All right, and then I've got a common denominator of h, so I'm going to write that as divided by h and then divided by h. And if you look at this expression, the limit as h goes to 0 of this is just the derivative of f. And then as h goes to 0, this is really just the derivative of g. So when you take the derivative of a sum, all you're going to do is take the derivative of f and add to it the derivative of g. All right, so another example of this would be, what if our function was, let's call it m of x, and let's say that m of x is equal to x to the, let's say x to the 3rd plus, and then let's make this other function, well, let's just say 1 over x to the fourth power. Okay, so this is the same thing as x to the third plus, and then remember we have to handle this as x to the negative 4. Okay, so our derivative rule says if I want to take the derivative of this function, all I got to do is take the derivative of this, and we would have m prime of x would be equal to 3x squared is the derivative of that, and then our rule just says take the derivative of the other one, which would be negative 4. X to the negative 4 minus 1 would be negative 5, and our answer would be just that, 3x squared plus negative 4x to the negative 5th power. Okay, so again, I think that this is fairly intuitive that you're going to take the derivative here to get this, and you're going to take the derivative of this to get this. All right, so if we go back to the original problem that we looked at, it was, what was the derivative of x squared plus 3x plus 2? Okay, so find the derivative. All right, so this is just 3 functions added together. We're going to take the derivative of each one individually. The derivative of x squared is 2x. Okay, plus the derivative of 3x. Okay, we had a rule for the derivative of x, and so this is just going to be 3 times the derivative of x, which is 1, and then the derivative of 2 is just 0. All right, and so you're going to end up with your answer is just 2x plus 3. All right, now the nice thing about that is, here was the first page we started with today. We said, find the derivative of this function. We went through all of this work and we came up with 2x plus 3, which is the same answer that we got here, only we got there a lot quicker. Okay? All right, so you've got a handful of rules that we went through today. The first one is, I think we should probably look at this as the derivative with respect to x. The first rule that's in your book is of a constant is 0. The derivative with respect to x of x was 1. Okay, then we had the derivative with respect to x of x raised to a power. And this is one you're going to run into over and over and over because we work a lot with power functions, is n x to the n minus 1. And then our more general rules are the derivative with respect to x of a constant times a function is equal to the constant times the derivative of the function. And then we've also got the derivative with respect to x of f of x plus g of x. And this is just f prime plus g prime. Okay, and I didn't mention this earlier, but if it works for addition, it also works for subtraction. Okay, so with these rules then, you've got a ton of different kinds of functions we're going to run into that are going to be of some form of this. The sum or the difference of some functions. Those functions might be constants multiplied by a function, and some of those functions might be power functions. Some of them might be square root functions. Some of them might be 1 over x raised to a power. Okay, all of those functions we should be able to find derivatives of. All right, and I just want to kind of give you a heads up also that throughout this chapter we're going to start adding to our list of different kinds of functions that we want to be able to take derivatives of. And in this section you've got these kinds of functions, x to the nth power. All right, now there's also another function in here that is the derivative with respect to x of a to the x power. All right, and more particularly, we're going to be looking at this one, the derivative with respect to x of e to the x power. All right, and I want to kind of quickly go through and talk about the derivative of these. All right, and so first thing I want you to recognize is that if we wanted to take the derivative with respect to x of e to the x, all right, a common mistake that students are going to look at is they're going to say, well, this is going to apply to the power rule. And they'll pull the x down and they'll make it x e to the x minus 1. All right, and I'm not going to write that down because it is not correct. This is a different kind of a function. The difference here is that we took the derivative with respect to x of x raised to a power. All right, so here the power is the variable, here the base is the variable. All right, this one is in x to the n minus 1. This one, we've got to do something different. All right, this is going to give me a function that is going to, it does work out really nicely actually, but we got to go back to the definition of the derivative and say the derivative with respect to x of e to the x by definition is the limit as h goes to 0, and it will be e raised to the x plus h minus e to the x all divided by h. Okay, just replacing the x's with x plus h and x. All right, and then I'm going to simplify this as much as I can. This is going to be the limit as h goes to 0. And if you remember your exponential rules, this is e to the x plus h is e to the x times e to the h. Okay, we add the exponents to get here, and then minus e to the x all divided by h. So we get the limit as h goes to 0. If you notice, you can pull out an e to the x, and you're going to be left with e to the h minus 1 all divided by h. All right, and the other thing is that this e to the x isn't dependent upon what's happening to h. So we could say this is the limit as h goes to 0, and then of e to the h minus 1 divided by h, and then that whole thing just multiplied by e to the x. All right, so I guess I want to know, what is this thing going to be? What is e to the h minus 1 divided by h? And there's not a nice way to do this algebraically, but I think I can convince you on the calculator that if we look at that function and put small values for h in there, we should get a pretty good approximation. All right, so let's say that we take e raised to the, I don't know, 0.1, and then minus 1, and then divided by 0.1. Right, and so that ends up being 1.05. Right, but you might say, well, 0.1's not all that small. Let's try a smaller number. All right, so let's plug in, instead of 0.1, I'm going to plug in 0.01 and divide by 0.01. All right, and then I get 1.0005. Okay, and if you make that even smaller, let's stick another 0 in here and make this 001. Okay, it looks to me like this number is getting pretty close to 1. All right, and so it appears that the derivative of e to the x is just 1 times e to the x. Okay, and so the derivative of e to the x is another one that we're going to want to know, and this is a really nice function because it's a nice function because the derivative is itself. All right, so the derivative of e to the x is just e to the x. Okay, which can be kind of a little bit confusing because sometimes we're going to be looking at these and saying, well, is that the derivative or is that the function? And so you got to kind of pay attention that this is the slope of the tangent line at that point, and it happens to be just equal to the value of the function. Okay, and then I want to look at, well, what happens if we have something else raised to the x power? Okay, like what happens if we wanted to take the derivative of 2 to the x? All right, so if we did that, the derivative with respect to x of 2 to the x, if you kind of follow through what we did with e to the x here, we're going to do the same thing with 2, and we're going to get the limit as h goes to 0. We'll have 2 to the x plus h minus 2 to the x over h. Okay, this is the same thing as the limit as h goes to 0. Rewrite this as 2 to the x times 2 to the h minus 2 to the x over h. This is the limit as h goes to 0. You can factor out a 2 to the x here, and you're going to get 2 to the h minus 1 divided by h, and then times 2 to the x. All right, so we're going to end up with a very similar expression here that we did up here, except now this is going to be a 2 instead of an e. All right, so if we go back to the calculator and suppose that I wanted to know what this number is, I'm just going to replace these e's with 2's, and we'll get let's see, I'm just going to clear that. So 2 raised to the small value for h is, let's say, 0.001. Okay, and then minus 2 to the 0, I should just say minus 1, and then divided by 0.001. All right, it looks like that number is going to be probably pretty close to about 0.693. All right, so 0.693 times 2 to the x power. All right, so it looks like that's the derivative of 2 to the x. All right, and then if I wanted to find the derivative of 3 to the x, we can do exactly the same thing. All right, now I kind of want to generalize this and say, all right, well, if we take the derivative with respect to x of 2 to the x, we're going to get 0.693 times 2 to the x. If I take the derivative with respect to x of, let's say, 3 to the x, okay, we're going to end up getting something that looks exactly like this, but instead of a 2, we're going to end up with a 3 here. All right, and so if I take this expression and I'm going to replace this 2 with 3, I'm going to get 1.099. All right, so this is going to be 1.099 times 3 to the x. All right, and if I take the derivative with respect to x, let's say of 4 to the x, all right, we're going to end up with 1.387. 1.387 times 4 to the x. All right, so what I want to know is, I don't want to have to memorize all these different numbers or look them up in some kind of a table. What I'd like to look at is, where do those numbers come from? All right, and I'm going to tell you just from inspection that if you take the natural log of 2, right, and there's no reason why you would ever think this, the natural log of 2 is 0.693. And if you take the natural log of 3, the natural log of 3 is 1.09, or 1.099. And if you take the natural log of 4, I think you're going to anticipate that that's going to be that number. All right, let's try it. Natural log of 4 is 1.386, or 387. All right, so it looks like this number that we're going to put out in front is just the natural log of the base. All right, so if we add to our list here, the derivative of a to the x is the natural log of the base times a raised to the x power. Okay, so I think with that, I'm going to see if we can take the derivative of a function, and let's say that this function is, I'm going to make it as messy as I can and still be able to come up with a derivative. Let's say x to the 4th plus, let's say 7 to the x plus, let's make this 1 over x to the 3rd plus, let's make this the 4th root of x plus 3e to the x. Okay, pretty messy function. All right, so we've got a rule that says that if I've got a bunch of functions added together, all I got to do is take the derivatives individually. So take the derivative. First one should be the easy one. That's going to give me 4x to the 3rd power. Now, this one is an exponential function, not a power function. So I've got to think of this as like a to the x. So the derivative of a to the x is the natural log of the base times the base to the x power. This one I want to think of as x to the negative 3rd power. Take the derivative of that using the power rule is going to give me negative 3x to the 1 less power would be negative 4. This one I want to think of as x to the 1/4 power. So we get 1/4 x, and then 1/4 minus 1 is minus 3/4. And then this last one, this is a constant times an exponential function. So we're just going to take the constant 3 and then the derivative of e to the x is e to the x. All right, so we end up with this derivative, and we get that using some shortcuts, and those shortcuts are just the rules that are in section 3.1. Okay? All right, so that should get you through 3.1, and I'm going to tell you that this is a really important section. I really want to encourage you to make sure you do all of the homework problems, and especially this time, you know, we've been moving along at a kind of a slow pace, I think, and we're going to start picking it up a little bit. And being able to get these rules down and being able to apply them is going to be really, really important in order for us to keep moving on, because we're going to end up using these throughout the rest of the semester. And so the quicker you can get these rules down, the better, right? And there's a lot of applications to these, so make sure that you're doing all the homework problems, and if you have questions on them, make sure you're asking. Okay? All right, so you all should be working on section 3.1. I'm going to put together another video and get that available to you probably over the weekend so you can work on that on Monday. And that's on the product rule and the quotient rule. And those are rules that are not quite as intuitive as the constant multiple and the sum and difference rule. Okay, so enjoy your weekend, and I will see you next week.